So welcome back, students. We'll start this video with an example problem. The example problem is 13.1. Let me read the problem. Given the mass of iron nucleus as 55.85 units, which is the atomic mass unit, and A is equal to 56, find the nuclear density. Okay, so they've given you the mass of the nucleus. Mass of the nucleus is given, which is 55.85 atomic mass units, and the mass number is 56. So this makes sense because you need to have an integer, a number of protons and neutrons. You cannot have a fraction of protons and neutrons. So here, when you say 56, 26 protons and 30 neutrons. So that makes 56. So this is the mass of the nucleus. We call this mass of the nucleus. So now you need to find the density of the nucleus. So how do you find the density? So very simply, the density of the nucleus is the mass of the nucleus is divided by volume of the nucleus. This must be in kilograms and this must be in meter cube. So what's the mass? So this is equal to mass is given to be 55.85 atomic mass units. So but you have to convert that into kilograms. Okay, so we've seen in the previous video that the one atomic mass unit is 1.66 into 10 to the power minus 27 kg. So one atomic mass unit is 1.66 into 10 to the power minus 27 kg. So mass of the nucleus is this, right? So 55.85 into 1.66 into 10 to the power minus 27 kg. So this is an atomic mass unit and this is in kg. So what do you will get? If I multiply these two numbers, then I'm going to get 92.7 into 10 to the power minus 92.7 into 10 to the power minus 27 kg. So that becomes 9.27 10 to the power minus 26 kg. That's the mass of the nucleus. So now I need to find the volume of the nucleus. So what's the volume? Volume of the nucleus is equal to 4 by 3 to pi r cube, where r is the radius of the nucleus. But what have we done in the previous video? We have found a relationship between the radius of a nucleus and the radius of individual proton or neutron, assuming that they are approximately at the same size. We said this r was equal to this r naught into a to the power 1 by 3 into so this is what we saw. Okay, I will not hit 4 by 3. So this becomes 4 by 3 pi into r naught cube, okay, into this will become a naught. Okay, because r can be written like this. So when you cube r, and this is what you're going to get. But what is r naught? You say that r naught is 1.2 into 10 to the minus 15 meters, right? So this is going to be equal to 4 by 3 into 3.14 into 1.2 into 10 to the power minus 15 meters. So that Q to A is the mass number. So the mass number is 56. So there are 56 of these things there. So we get this, and then if you find rho, it's going to be this Mn by V, and that's going to give you 9.27 10 to the power minus 26 divided by 4 by 3 to 3.14 into 1.2 into 10 to the power minus 15 the whole cube into 56. And if I do that, so this is going to give me this value, 2.29 into 10 to the power 17, 2.29 into 10 to the power 17 kilogram per meter cube. So it's enormous, the density is enormous, and we also said that the density of the nucleus is equal, roughly equal to the density of an individual proton or neutron. So that's what we get. There is an important concept that we need to talk about now, which is Einstein's mass energy equivalence. Einstein said that energy and mass are the same things. Okay? Energy can be converted into mass, and mass can be converted into energy. So they may appear to be different, but basically, if I get rid of mass, then I will get energy, and if I get rid of energy, then I can convert that energy into mass. So that equivalence, this mass energy equivalence, is given by the most famous formula in the entire world, okay, which is E is equal to mc squared. Okay. So where E stands for energy, M stands for mass, and C is the speed of light in vacuum. So if I have a certain amount of mass, I can convert that into energy. Then once I convert it into energy, the mass will vanish totally. You will get energy. So that's what it means. Or if I have energy, then I can convert it into mass. So, for example, like if you have say, if your mass is 50 kg, suppose if I get rid of you, okay, you completely vanish. You're not present at all. No atom of your body is going to exist after this process of converting you into energy. Then if I do that, then what kind of energy are we going to get now? What is the amount of energy I can get by taking a body of mass 50 kg and converting it completely, totally into energy. And once this conversion is over, the mass is not going to be available. It's going to be all energy. Okay. So what is the amount of energy this body will contain? Let's do this. If M is equal to 50 kg and C is 3 into 10 to the power 8 meter per second, then energy, by converting this completely, this mass into energy, it's going to be M is 50, C is 3 into 10 to the power 8, the whole square. So many joules now. So this will be 50 into 9 into 10 to the power 16 joules. So this will be 450 into 10 to the power 16 joules, or 4.5 10 to the power 18 joules. That is an enormous amount of energy. An enormous amount of energy can be released just by taking a mass of 50 kg and converting it completely into energy. It's a lot of energy this is. Okay. So This equation plays a very crucial role in our understanding of nuclei. First, let's do a problem, example problem, and then we'll proceed with that. I'll do example 13.2. Then it says calculate the energy equivalent of 1 gram of substance. We've done it for 50 kg. So 1 gram, it's very, very easy. So let's do that. 1 gram. So that is 13.2. Mass is equal to 1 gram or 10 power minus 3 kg. Then energy is equal to mc squared. So if we make this vanish completely and get energy out of it, then it's going to be m is 10 power minus 3. But this is going to be 3 into 10 power 8 the whole square. So 10 power minus 3 to 9 into 10 power 16. So energy you're going to get so many joules. It's going to be 9 into 10 power 13 joules. Again, it's enormous amount of energy. A lot of energy this is. Just 1 gram can produce a lot of energy. Take 1 gram, make it vanish, then you can produce this amount of energy. This mass energy equivalence is a very, very, very important idea, and that helps us, as I said, understand what happens in a nucleus, basically. And this helps us build nuclear, the atom bombs, okay, and then the nuclear reactors and stuff like that. This helps us do that. We'll see how now. Okay, let's take an atom. In this case, it's going to be oxygen. I'll take oxygen now. So, oxygen has a nucleus, and in the nucleus it has 8 protons and 8 neutrons. They combine to become the oxygen nucleus. See, before we even talk about it, let's think about this. If you take oxygen, you have 8 protons is what I said. And how can you put 8 protons together? You need to understand this question. The reason I'm asking this question is this. If you take a proton and if you bring another proton near it, then what's going to happen? They're going to repel each other. So you have 8 protons together in the nucleus. So if you have 8 protons there, then clearly they will repel each other. And how can the nucleus be stable with this? How can you have a nucleus? That they should repel each other, they should fly away from each other. So you won't have a nucleus. So to keep these 8 protons there, and there must be something else. Okay, there must be another force which should overcome this force of repulsion. And that is given by the neutrons. If the neutrons are not there in the nucleus, the protons will repel each other and fly away. So the nucleus will not even exist, as I said. If the nucleus doesn't exist, then you can't have an atom, basically, except hydrogen atom. Because hydrogen atom, you have only 1 proton, so there is nothing to repel. But beyond hydrogen, the moment you talk about helium and other things, you got 2 or more protons. And the moment you have more protons, then you're talking about the electrostatic repulsion. If they repel each other, then how can you even have a nucleus? But then you have a nucleus. So this force, the repulsive force, the electrostatic force of repulsion has to be overcome by something else. And that something is what is called as the nuclear force. There are strong nuclear forces and weak nuclear forces. Let's not worry about them now. So the nuclear force, So the nucleus must have an attractive force. If it does not have this attractive force, then you cannot hold these protons together. So the force of attraction must be so big that it should be able to overcome the electrostatic force of repulsion. The nuclear force of attraction must be very big, like it should be large, be huge, to overcome this electrostatic force of repulsion. It is like the earth. Okay? Think about it. Okay, in the other way. You and I are masses basically. So you and I must attract each other. But when we are here together, we don't get attracted to each other. The masses don't attract. Maybe like if both of us are taken and then put in the interstellar space where there is literally no gravity, then both of us will come together and then stick to each other. The masses will attract. But on the earth, it doesn't happen. The reason it doesn't happen, even though there is a force of attraction between you and me, is that we are talking about another big mass, which is the earth. The earth is attracting me, you are being attracted by the earth. So the force of attraction between you and the earth is much greater than the force of attraction between you and me. And the same thing holds good for me too. The force of attraction between me and the earth is much greater than the force of attraction between you and me. So this is something similar. In the nucleus, the protons will try to push each other out. They'll try to repel each other. It's very, very, very strong. It has to be, right? You know, because they have some electric charges, and then they are constrained in a very, very small space. So small. Even if you take the example that we just did for the density of the nucleus, we are talking about a radius of 1.2 in 10 power minus 15 for a proton, and then another 1.2 in 10 power minus 15 for a neutron, for another proton. So even if they are together, so you're talking about like 2.4 in 10 power minus 15. So that is the distance between each of them, between the two protons. So it's a very small distance. So the electrostatic force of repulsion has to be huge there. But they are there together. And now, if you take oxygen, it's not just two, right? There are 8 protons. So if you take one proton, then there are 7 forces acting on this from the other 7 protons. This is what's happening there. So the force of repulsion is huge on each proton. But despite this huge force, they are sticking together. The reason they are sticking together is because there is a force of attraction given by the neutrons and the protons and stuff. Okay? There is a force of attraction between neutrons and neutrons, and the force of attraction between neutrons and protons. Of course, there is no force of attraction between protons because protons will repel. So if you have a neutron, this neutron will attract a proton, and then this neutron will also attract another neutron. Okay, so and this is what we call as the nuclear force. This force of attraction is huge. It has to be huge, very, very, very strong, to prevent these protons from flying away from each other. I want you to understand that. Okay. So once you understand that there is an electrostatic force of repulsion among the protons, and there is also a nuclear force of attraction among protons and neutrons, then we are good to go. We can go to the next level. Now we'll talk about the oxygen atom. Okay? So say the oxygen atom, the nucleus, you have 8 protons and 8 neutrons. So take oxygen. This is 8 protons and then 8 neutrons. So let's say what is the mass of this solid? Okay, so you know that a proton must have a certain one proton. I'll say mass of proton is equal to 1.00727 atomic mass units. If you convert that into kilograms, but that's different. Mass of proton is this. Then mass of neutron is equal to 1.00 to 866. You saw that. And if you also take the mass of electron, it's going to be equal to 0.00055 atomic mass units. So this is the atom. Well, so the expected mass of the neutron or the nucleus, I'll say, the expected mass of the nucleus. So if I have the oxygen atom, so you have the nucleus here, and then here. So that's how it is. 2 here, and then 6 here. So the expected mass of the nucleus alone. So the mass of the nucleus, called as capital M to N. This is mass of the neutron, but this is mass of the nucleus. Okay, and this is equal to 8 times the mass of the proton plus 8 times mass of the neutron. Okay. So that gives you 8 into 1.00727 plus 8 into 1.00866. So that gives you totally 16.12744 mass units. So if I have 8 neutrons and 8 protons, and if I calculate the mass of them all, then this is the mass I should get. And then if I also add the mass of the 8 electrons here, then I will get the mass of the entire atom. And this would be the mass of the nucleus. This is what I should get. Okay. But when I measure it, when I actually weigh the neutron, okay, of course indirectly, so when I weigh the mass of the neutron, I get this value. I get oxygen. This is theoretical. This is mass of the neutron. This is actual. This is what I should get, right? If there are 8 protons and 8 neutrons, and if I know the mass of proton and mass of neutron, this is what I should get. But when I actually weigh the mass, weigh the neutron, weigh the nucleus of oxygen, I get this value, 15.99493 atomic mass units. This is what I should get, but this is what I get, I actually get. So you can see that the theoretical mass that you calculated is 16.13 roughly, and the actual mass is 15.99, maybe 16. So you have 16.13, and then roughly, I mean, you have to calculate exactly, because even 1 gram, can produce a lot of energy. But let me still ignore that and then say it is 16. So 16.13 and then 16. So there is a difference of 0.13, and that's close to like 1% of the mass. You can do the calculation exactly, but then it's nearly like 1% of the mass. So if you bring 100 units of mass, and close to 1 unit is gone, so only 99 is remaining. You expect this to be 100, but then you get only 99 there, so there is a small difference in the mass. So Einstein said this. Einstein said, when you bring these things together, when you bring protons and neutrons together to form the nucleus, then what happens is that part of the mass of these things, these particles, will get converted into energy. So when you fuse them together, then there is an energy release from that process. So that energy has to come from the mass of the protons and the neutrons. A part of the proton and the neutrons are getting converted into energy. So what you have in the nucleus is a remaining mass. So it is like this. Okay, you have a proton, and then you bring a neutron or something. Okay, you try to fuse them. And what happens is, you see, there is this part, and that's gone. Okay. So you lose a little bit of mass from this and a little bit of mass from that. So now they are fused, but that mass has been released as energy. Okay. So clearly, you are not going to have the mass of the two nucleons. If you call them as nucleons, the protons and the neutrons have a common name. They are called as nucleons. A proton is a nucleon, and then a neutron is also a nucleon. Okay? Anything that is in the nucleus is called as a nucleon. Okay? So you bring two nucleons, then you have this. The mass is always greater than once it's joined. So there is a mass. You call this difference in the mass as the mass defect. Okay, the mass defect. So the mass defect is the difference in this mass and this mass. What you are supposed to have and what you actually have in the nucleus. That's a mass defect. And mass defect, that mass is what is getting released as energy. So let me take a general case. If I take a certain atom, okay, if this X. So what is the mass of X now? So the mass of X, this is the theoretical. Okay, let's put this way. Let's say mass of X theoretical is equal to the number of protons into mass of protons plus the number of neutrons into the mass of neutron. That's the theoretical mass. Okay, so I can do it slightly differently, because what is the number of protons? Number of protons is actually the atomic number, right? So that is going to be Z into mass of proton. And what is this number of neutron? Well, that's the mass number divided the atomic number subtracted from the mass number, right? So number of neutrons is going to be this, right? This is the mass number minus the atomic number. So that will give you the number of neutrons. So this is the theoretical mass this is the mass we expect in the nucleus. Then there is this actual mass, right? That actual mass, I'll call it as MA, is the actual mass. Okay, So the mass defect is the difference between these masses, what you expect to have and what you actually have. So the mass defect delta M is equal to mass that you expect for the element X and then the actual mass of the element X, AX, AX. Okay? Alright, yeah, well, just a simple solution matter. So this gives you, so Z MP plus A minus Z into Mn, that's the expected mass minus the actual mass. So this is the delta. So this is the mass that's gone, it's not there now. So this is the mass you expect to have and this is the mass you actually have, which means that when this nucleus was formed, this amount of mass was converted into energy. So the energy released when the nucleus was formed was equal to, energy released was equal to delta M to C square. So when the nucleus formed, this energy was released. So when the protons and neutrons came together, they got fused into the nucleus of any atom, in this case oxygen, it's true for any atom. When they did that, this amount of energy was released because that mass is not there. A certain amount of mass is missing, so that must have gone out as energy. This is what Einstein said. Okay. Well, how do you prove that? Well, the thing is, if I have to break this now, okay, suppose I am going to break this nucleus into its constituent parts. If I break this, then I would have 8 protons and then 8 neutrons. That's what I should have. But look, now you have a partial proton. See, the proton is not full. And then you also have a partial neutron there. If you break, then you will have a partial proton out, and then can you have a partial neutron, like it's 0.9 neutron out, or 0.99 proton out. Can that happen? A proton is one proton. You cannot have a 0.99 proton out. When a proton comes out, this is what it should weigh, right? This is what it should, The mass of the proton must be this. But then you don't have that mass here. So what you have to do? You have to provide this amount of energy to it. When you provide this amount of energy, the missing energy, when you provide that energy, then the nucleus takes that energy, converts that into mass, and it breaks. When it breaks, then you get a whole new proton. Okay. So when it formed, it converted part of its mass into energy. Now that mass is not there, but now you are going to break it. But when you break it, you must have one proton. You cannot have 0.99 proton. You must have one neutron. That's what will be out. So you need to provide the missing mass. How can you provide the missing mass? You can provide the missing mass by giving it the missing energy. You give it the missing energy, or the energy that is supposed to come out when this was formed. So you provide that energy, and that energy gets converted into the required mass, and this breaks into its constituent parts. Then you get 8 neutrons and then 8 protons. Okay. This energy, this delta mc squared, is called as the binding energy of the nucleus or the atom, because this is the energy which is required to be released to bind the nucleons into the nucleus. Okay. So this is called as the binding energy. Now this is the binding energy of the nucleus. And then different nuclei will have different binding energy. For example, if you have oxygen, then you will have a certain amount of binding energy. And if you have nitrogen, that will have a different amount of binding energy. And then if you have iron, it will have a different amount of binding energy too. Because now there are many things which are coming together. So each of them will lose a certain amount of mass in them. For example, like if you take iron, let's see, I'll do it here. Iron is 56, right? So you have 30, 26, this is 56. So 26 protons and then 56 nucleons, meaning 30 neutrons and 26 protons. So 56 nucleons. This is protons. So then, which means 30 neutrons. Okay, so 30 neutrons. 30 neutrons is what I get. Okay, so all these things come together, so that they will bind. When they bind, each of them will lose a certain amount of mass. And since each of them loses a certain amount of mass, then there are 56 of them, right? There are 56 of them, each will lose a certain mass. So the amount of mass that is lost in iron is much more than the amount of mass that is lost when the oxygen nucleus was formed. There are only 16 of them. There are 56 of them coming together. And when they come together, each of them must use a certain amount of mass. So the energy released when the iron atom is fused is much greater than the energy that is released when the oxygen nucleus was formed. So if you want to break this oxygen, then you need to give a certain amount of energy. Whatever energy that was lost has to be given now. So that the nucleus will now take the extra energy and form its neutron and then proton in whole and put it out. But you have to provide much more than this energy to do the same thing with iron. Because iron nucleus had given out lots of energy when this was formed. So now, if you want to break it, then you need to provide a lot of energy. Then the nucleus will take this energy and convert it into mass and provide that mass to its nucleons, the protons and then the neutrons. And then the protons and neutrons will have the amount of mass that they had lost and come out as a whole. Okay. So the binding energy for iron will be greater than the binding energy for oxygen, merely because of the size of the atom. So the bigger the atom, the binding energy of the atom is going to be bigger. The bigger the atom, the bigger the binding energy of the atom. The atom as a whole. Simply because you have a lot more nucleons in a bigger atom than a smaller atom. I hope this is clear to you. Now let's do example problem 13.3. Let me read this problem. Find the energy equivalent of one atomic mass unit. Find first in joules and then in mega electron volt. Using this, express the mass defect of oxygen in mega electron volt per c squared. Okay. Read the problem again. Find the energy equivalent of one atomic mass unit, first in joules and then in mega electron volt. Using this, express the mass defect of oxygen in mega electron volt per c squared. Okay. So what is, do 13.3. So what is this? First one is one atomic mass unit. So one atomic mass unit is equal to 1.66, well, I'll take some more, okay, 0.5 into 10 to the power minus 27 kg. So this is the mass of one atomic mass unit. Okay. Then what's energy equivalent? Well, if we convert all of this mass into energy, how much of energy I would get? Okay, so that would be, you know that E is equal to mc squared. So we're going to convert all of this mass into energy. So that's going to be equal to 1.6605 10 power minus 27 into c squared, 3 into 10 power 8 the whole square. Okay, so that, so many joules, right? So this actually gives me 1.4924 into 10 power minus 10 joules. It's not a lot. You can see that it's not a lot. Okay, but then the one atomic mass unit, if it is made to vanish, then this is the amount of energy it's going to give. This is in joules. But what is the same in mega electron volts? Well, if I have to express it in electron volt, then this is going to be 1.4924 10 power minus 10, so divided by 1.602 into 10 power minus 90, and this would be in electron volt. Okay. And this would give me, how many electron volts? This is going to give me 0.9315 into 10 to the power 9 electron volt. So one atomic mass unit, can be converted into so many electron volts. So then how many mega electron volts are there? So again I need to divide that by 1 million, right? So it's going to be 0.9315 into 10 to the power 9, so divided by 10 power 6, that is mega electron volt. So many mega electron volts. So that gives me 10 power 3, so 0.9315 into 10 power 3 mega electron volts, or if we multiply that, it's going to be 931.5 mega electron volt. So if you take one atomic mass unit and if you make it disappear, we convert all of it into energy, then this is the amount of energy that will be released in the process, as per Einstein's mass energy equivalence equation. Okay, so that's the first part. The second part is, using this, express the mass defect of oxygen in mega electron volt per c squared. Okay. First of all, so what's the mass defect here? So what's the mass defect here? The mass defect, like we just discussed, you were supposed to get 16 point, so mass defect delta M was equal to the calculated mass, now in this case oxygen. Now the actual mass of oxygen, so this was 16.12744, and what she actually got was 15.99493 atomic mass units. So that is equal to 0.13691, 0.13691 atomic mass units. Okay, so this is delta M. So what do you know? Well, if I convert that into energy fully, then how many mega electron volts will I get? That's the question. Okay. So if you convert this, then what would I get? For one U, it's equal to 931.5. So this is equal to the amount of energy contained in this is what? This energy is equal to delta M C squared, right? So this is equal to 0.13691 unit into 931.5 mega electron volt, right? So for 1 unit, this is mega electron volt, right? So then it's going to be, this is the amount of energy this is going to contain. Okay, so this is what it is. So the energy equivalent of this delta M is given by 127.5. If I multiply this, then it's going to be 127.5 mega electron volt. That's the amount of energy in this. Okay, in this delta M. So this delta M contains this, and this is actually delta M C squared, right? So what is delta M? So delta M is 127.5 mega electron volts per C squared. Okay. So this is how you do this problem. Okay. The simple idea is this. Einstein came up with this mass energy equivalence. The equation for that is E is equal to mc squared, the most famous equation in the world. Everybody knows it, even Nityananda knows it. So, rather, he doesn't agree with that equation, but that's a different story. But everybody else agrees with it. So, E is equal to mc squared. Except Nityananda, everybody else agrees with that equation. So, E is equal to mc squared. So, that is the equation we are focusing on. Okay. That equation helps us understand what happens in the nucleus. So when you look at the nucleus, then you know that there are a certain number of protons and there is a certain number of neutrons in the nucleus. So if you take the number of protons and then find the mass of the protons, and then if you take the number of neutrons and find the mass of the neutrons, if you add them together, that should be the number of the mass of the nucleus. Theoretical mass. This is what you expect to have, because there are n number of neutrons and then m number of protons. So you need to get this mass. But when you actually weigh the nucleus, you don't get this mass. You get mass which is less than the calculated mass. So there is a difference between the mass that you expect to see there and the mass which is actually there. And this difference between expectation and the actual values is called as the mass defect. So this amount of mass, the defect, the delta M, is not there. It should have been there, it is not there. And what Einstein said was this delta M was converted into energy. okay, when this nucleus was formed. So a part of this mass, the combined mass, was released as energy. So if you want to break this nucleus into its constituent parts, as individual neutrons and protons, then you have to supply the energy that this process had released. So you have to supply this energy. Then when you supply this energy, then the nucleus takes that energy, converts it into mass, and attaches that mass into these different components, the constituents of the nucleus, and then when they come out, then they come out as a whole. Okay, you will get a whole proton, a whole neutron when they come out of this. So for that to happen, you need to provide energy. So when you provide energy, it gets that energy, converts it into mass, puts it out. Okay? So this equation E is equal to mc squared helps us understand what's going on. And then we also talked about binding energy. So binding energy is required. Why? So because of this, right? Like when they come together, certain amount of energy is released. So each of them, each nucleon loses a certain amount of mass. So the bigger the atom, the bigger the nucleus, the greater the binding energy for that nucleus, for the nucleus as a whole. Okay? For the nucleus as a whole, because it's bigger, then it's going to be the binding energy for the nucleus is more. Okay? So iron, for example, would have a greater binding energy for the nucleus than that for oxygen. So oxygen has only 16 nucleons, but iron has 56 nucleons. So when iron was put together, a lot more energy would have been lost than when oxygen was put together. So this is the simple idea, and the whole lesson is based on this. Hope you understand this.